Okay, so a charged particle here, a negatively charged particle, and a positively charged particle, and the electric field that results in between them, this modification of the area between and around, and theoretically often to infinity, out here somewhere, theoretically. It's obviously extremely weak the further you get out. These two charged particles here are both positively charged, or they have the same charge, and so their electric fields are kind of repelled. Remember also that these electric field lines from the last lesson may not cross at any stage. Okay, theoretically, once again, going off into infinity. Here, this diagram here, I'll just make it a little bit smaller. This, actually, I better make it a bit of a different color, I think. This here, this thing, there, is theoretically an infinitely charged plate. It's some sort of a conductor. Think of it as a piece of copper, say. Say it's a plate that goes off to infinity in all in 2 dimensions. Okay, and it's positively charged. So they've got all of these plus signs in here. Okay, to say that it's positively charged. There. This one here is the same situation, except it's negatively charged. Now you might notice these things outside the infinite plate. These things here. What's this? This is the electric field. Notice that if I put a small positive test charge in anywhere around this plate, that small positive test charge would go off in a direction away from the plate, and that's why the arrows are pointing away, right the way along the plate. What do you notice about the electric field around this infinitely charged positive plate? It is uniform. Yes, it appears to be uniform, doesn't it? There's no curvature of these electric field lines. They are equally spaced, and theoretically they are uniform. I will state that. The one thing you might have also noticed about the charges, these positive signs, they're saying that this plate is positive. Think of those positive signs as charges within the plate. What do you notice about them? Yeah, the charges, what do we mean by uniform there for the charges? Yeah, are equally spaced. Why do you think that is? Yeah. The charges are equally spaced. And this is very intuitive. Of course, if I have a positive charge next to a positive charge next to a positive charge, they're equally repelling each other. They're confined to the copper plate, but they repel each other evenly all over that plate. They spread evenly all over that plate. Okay? Because of that, there's no concentration of positive charge anywhere on the plate. It's all just nice and evenly spaced, and hence we have this uniform electric field around the plate. Same with the negative plate, except for the negative plate, of course, if I were to put a small positive test charge around that plate, I would notice that the small positive test charge moves toward the plate. That's the only difference there. Okay, charges are equally spaced within the plate. Electric field is uniform. Um, Here we have a different situation. Infinite, oppositely charged parallel plates. What do you notice about this situation? Who wants to make a comment on the situation here? Ah, interesting. Yes, no charges outside the plates. We don't have, oh sorry, no electric field outside the plates. Yes, no charges outside the plates, but yes, that's true. No, that's true also. The charges are confined to these plates still. There's no electric field outside the plate. Remember, this plate and this plate both go off to infinity in 2 dimensions, effectively filling up the XY axis. So, can anybody see why that might be? Why would we see no electric field outside the plates, but we see an electric field inside the plates? Ah, how do they cancel each other out? So the electric field on the outside cancels each other out. Yeah, uh, yeah. Ah, right. Okay. Yes, that people will understand better, perhaps, Andrew. I think so. If we if we have a look at, imagine there's an electric field outside here. Okay, and it's directed, of course. If we put a small positive test charge, then I can say that it's directed towards that negative charge there. There's an electric field outside also due to this positive charge, isn't there? The electric field on the outside on this side of the plate due to that positive charge looks like this. Okay? The electric field due to this negative charge looks like this. And the electric field due to this positive charge here looks like this. Because theoretically, the electric field due to a charge goes off into infinity, doesn't it? If these are pretty close together, if these plates are very, very close to each other, in the situation like a capacitor, for instance, then this vector here, this electric field vector here, cancels out that electric field, and there is no electric field outside the plates. Yes. Theoretically, the electric field for each charge extends to infinity. No, it will not. It'll vary with a relationship of 1 on r squared, of course. Absolutely. Yes, absolutely. So the comment is, of course, because of the difference here, this distance, imagine it was that distance there, then of course the electric field due to the negative charge is going to be slightly stronger than the electric field due to the positive charge. And yes, we'll have a net electric field due to the negative charge there, yes, theoretically, but we're going to ignore that. Okay? For simplicity's sake. Oh, but because the lines are equally spaced. But imagine, although the electric field goes off to infinity, because of this, think of this situation here first with the positive charge. That charge there, what force does that little positive test charge experience due to that positive charge there? It is a repelling force, isn't it? And how would I make a quantitative statement about it? KQ F equals KQ on R squared. Okay. What does it say? However, at any point the field strength, is constant. The force on the charge due to an infinite plate will be constant. Oh, well, that's a little bit ambiguous. Hang on a second. The electric field strength is KQ on R squared. So it varies. It varies due to this this value of 1 on R squared. Okay, so the further you get away, the weaker the field strength. What I would like you to remember for the purposes of the course is, hang on, where was I? I'm deleting something here. There. What I would like you to remember is this. The electric field between the two plates is uniform. There is no electric field. Andrew, if you can prove that to me, I'll include it in the course. Okay. Prove it. You've got to prove it mathematically. What's that by tomorrow? There's your homework, yeah. Okay, so no electric field outside the plates. Here's another situation that you do need to know about. Whoops. Oh no, what did I do? It's all right. Sometimes it goes haywire. This situation here, they may ask you to draw in the exam, or I might ask you to draw in the test or the exam. Two non-infinite parallel plates. This is what they look like. What do you notice about this situation? Yeah, the physics terms. Physics terms. Yeah, curved field lines at the edge. What can you say about those field lines at the edge of the plates? So they're non-uniform. Yes. I better put in blue, two non-infinite plates. Infinite or finite. Two non-infinite parallel plates. The field inside between at the ends, the field is not uniform. You might be able to say that you do need to be able to draw that. That is part of the course, that diagram there, if necessary. Electric fields and other conductors. Conductors contain delocalized electrons. This is true of any metal in our experience. In fact, most any substance is a conductor at the right voltage. But good conductors, we're talking about good conductors. Metals, copper. I think silver is one of the best. Gold is one of the best also, but of course very expensive. Copper is becoming more expensive. Delocalized, some people, you might know it as, or the chemists might know them as free electrons. They're not tightly bound to any particular atom, and therefore they're free to move within the conductor. So in the situations that we saw here, this infinite plate or these finite plates here, the the charges move freely within the conductor until they are equally repelled across the conductor. Okay. We know also this situation, if I have, who's played with a Van de Graaff generator? We might have to play with one. Van de Graaff generator looks something like this. And this, of course, at the top, what we have is a hollow metal sphere, usually made of aluminium. There's probably better conductors, but aluminium's reasonably cheap and abundant. So we make the spheres out of aluminium. In here, we have something that's not such a good conductor, usually a piece of rubber in a belt. And what that belt does is it's connected to, at the bottom and the top, it's connected to an engine, a little electric motor that makes it rotate. This rubber, it's kind of a rubber band, I suppose. It's a very large rubber band, and this rubber band rotates. At the base here, it rotates very close to like a comb sort of a thing, or little hairs that'll allow charge to pass onto the rubber band. And at the top, some other little hairs that take that charge and distribute it onto the metal sphere. The metal sphere is insulated, other than the connection between the hairs here and, of course, the rubber band. The rubber band isn't a very good conductor, so it tends to hold charge until it reaches the hairs at the top here. What we will see, and I don't know what charge is put onto, I don't know what type of charge is put onto our Van de Graaffs here, but let's say it's positive charge. So we have these charges are distributed to the metal sphere. What is it that makes a Van de Graaff generator have a net positive charge? What's going on? So removing electrons. We can't cause any nuclear reactions that would change the positive charges within the atoms that make up the aluminium sphere. But we can cause chemical things to occur, chemical reactions, I guess, to occur. It's not a chemical reaction. We've got free electrons on this metal sphere, this conductor. It's very easy for us to drag some of those electrons onto this piece of rubber and distribute them down here to this hair and leave a net positive charge. So we all know that inside the atom, we have a positively charged nucleus. This is true of all atoms. And around the outside, we have electrons buzzing around, and they are negatively charged. We can't remove the positive charge from the nucleus, but we may be able to remove the negative charge, which is the electron. And so that's what we're doing here in this situation. How would we get a net negative charge on the sphere? Yeah, giving electrons to it. So we would distribute more electrons on there, giving the sphere a net negative charge. Okay? What do you think those charges do once they hit that sphere? Yes. They do. They distribute evenly around the outside. So once charges, and that's negative charges, are either distributed on the sphere or taken away from it. The sphere has a net charge, positive or negative. Those charges then distribute themselves uniformly around the outside surface of the sphere. And that's quite intuitive. They're all repelling each other. Of course, they're being repelled from each side. They kind of, yeah, they want to get as far away from each other as possible. And of course, so they end up on the outside of the sphere here, evenly, all over the sphere. A good question is, how is it that positive charges distribute themselves evenly? A net positive charge. Has anybody got an answer for that? If it's delocalized electrons, how is it that a net positive charge distributes itself evenly across the sphere? Positive ions, but it's a solid. The sphere is a solid. There's still electrons that make up the atoms, isn't there? And those electrons distribute themselves evenly still, still resulting in a net positive charge. Okay. There a couple of things we need to note. There is no field inside the conductor. If there was a field inside the conductor, then the charges would move with that field as a result of that field. They would be applied a force, F equals EQ, so there's no net field in the conductor. What about inside the conductor, in this hollow area inside here? What's going on in there? Nothing. True. Electric field wise, there's nothing going on inside there. Well, there is, but the vectors are cancelling each other. And so there is no I'll say net field inside the hollow conductor. That's true of any shaped hollow conductor. It doesn't have to be spherical. Not net field. Oh, yeah, thank you. There's no net field inside the conductor. Here's a portion of that sphere. Say we have positive charge. Actually, I'll draw the positive charge on the inside, although that's technically not true. Positive charge all over the sphere. Of course, there's an electric field. Have you ever seen the any way of seeing the electric field around a Van de Graaff generator? So somebody's seen it, have they? What it looks like? No. If you guys are cold back there, you can shut those windows. Uh, it looks like this. It just goes out from the sphere, and something very interesting. It meets the surface of the sphere at right angles. Always at right angles. Why? Has anybody got any ideas on that? Why electric fields meet the conductive surface at right angles? Yes. Uh, okay, yeah. So imagine what. So if there were lots of if I made this denser, then there'd be an electric field right next to it. Yes. And so they kind of, okay. So that is true, but it doesn't explain it the way I wanted it to explain. Yes. Yes. Yeah. So yeah, it is that. Okay. So, and that's another way of saying it, but and closer probably to what I was looking for. If I put a small positive test charge in here, it moves directly away from that as quickly as it can in a straight line path, doesn't it? From this positive charge, and so that happens to be at right angles to the surface too. Say this, physics terms. Uh, there is no force parallel to the conducting surface. So what I mean by parallel, if you take one very small place parallel to it is around that way, there is no force in those directions. And you guys have both said that in different terms. But if you were to answer a question about why electric fields meet conducting surfaces at right angles, that's what I would like you to say. Um, your page. Can I take this away? Yes. Yes, absolutely. So, yep. So that's interesting. Comment is if we have a Van de Graaff generator here with a positive charge, or any charge for that matter, with a net charge over it, what's going on with the surface or the fluid around that? Of course, we have air particles, don't we? Our gas around the Van de Graaff generator. So we'll call that air, which is lots of different gases. And yes, it does. What are they going to do? They're going to strike that surface occasionally, or rather not strike it. They never really touch it. They come very close to it. What happens when they come very close to it? They, yeah, they ionize, exactly as you said. They ionize. They have a more positive side and a more negative side. And the more positive side is repelled. So I'll see if I can go and find a video. This is a practical that we have done in the past. You may have seen this. Semolina in oil. Oh, yes. Here this looks like a positive electrode and a negative electrode. Sorry about the music. Oh, is it? Oh, it is a bit slow this morning, isn't it? Sorry about this.